All right, we're going to now go over the main types of energy. And again, this is going to be kind of brief because part of your work for this unit is going to be making infographics, and then we're going to be looking at everyone else's infographic. So that'll give us a little bit more of the information. We finished last time by going over kind of the general structure using coal of how we're going to get electricity, which is our usable form of energy in homes from coal. So make sure you go back to that if you need to. Coal is a solid fuel. It's formed primarily from dead plants that were preserved 280 to 360 million years ago. So when people say, coal is dead dinosaurs, most of it is not. Most of it is plant matter. Because there was so much more plant matter than animal matter around at the time. Kind of like today, we have lots of those primary producers. That triangle, the energy triangle, remember you have all the things at the bottom are all of the primary producers. Those are your grasses, your trees, whatever it is. 4 types of coal ranked from lesser to greater age, exposure, pressure, and energy content are lignite, subbituminous, bituminous, and anthracite. So these are our 4 types of coal. Basically, as you change from one to the other, you're getting older coal, and you're getting more energy content. So there are your 4 types. The largest coal reserves are in the US, Russia, China, and India. So the US has a bunch. Canada has a bunch of coal in a slightly different form. Russia has a bunch, and so does China and India. You'll notice that these countries are also pretty large countries. So they have more space in order to find some of this. But it also depends on the geology and what kind of rocks are there. All right. Mining in Appalachia. Most of the mining has been done using mountaintop removal. Mountaintop removal is a form where you basically take the top of the mountain. This means you're destroying a bunch of the trees and ecosystems that are there. In addition to that, a lot of times you have a lot of waste that's not being used, and some of that is going to have toxins in it. As you break up some of that rock that's in the mountain, it might have some of these heavy metals and things in there that can then get into water. In 2010, so this is relatively recently, the EPA banned valley fill, where the mountaintop rubble is just dumped into the valley, which in effect destroys 2 habitats because it destroys the valley habitat and the mountaintop. Existing mines, however, were grandfathered in, so they were still allowed to finish up the valley fill. Mine reclamation is mandated in the U.S., so we have that Surface Mining Control and Reclamation Act of 1977 that mandates reclamation after mining. Depending on the type of coal, so up here, your lignite, subbituminous, bituminous, and anthracite. Our anthracite is typically going to be most energy rich and also cleanest burning, so it has fewer impurities. And the impurities we most often see in coal are things like mercury, arsenic, chromium, lead, and uranium. Sulfur dioxide and nitrogen oxides are released into the air during burning. That's part of our air pollution. Those are some of those primary air pollutants that can then cause smog as they react with other things to become secondary air pollutants. And the use in the US is declining, despite the fact that we have a lot of it, in part because of renewables and natural gas are much cheaper. And there's this movement towards clean coal, which is technology to preserve jobs in the coal mining industry while helping the environment. So part of this is carbon capture and storage. So this would reduce the release of CO2 overall because we would be capturing some of it and storing it. Reduce emissions of the sulfur dioxide and NOx. And that can be done with a couple different kinds of air purifiers and things, which we'll talk about. And then integrated gasification combined cycle combustion, which is a big mouthful. Basically, you heat coal with pure oxygen at high temperature so that it doesn't burn, but it reacts with the oxygen and breaks down into hydrogen and CO2. The hydrogen can then be burned cleanly, but it is highly explosive at that stage. So the integrated gasification combined cycle combustion really has to be done very carefully. It can allow us to burn the coal more cleanly, though, which reduces the release of some of these other gases. Generation, so using coal, burning fuel from coal transfers energy to water, which becomes steam. That's that diagram we looked at. The kinetic energy contained within the steam is then transferred to the blades of a turbine. The turbine has this kinetic energy now, and the shaft in the center turns the generator, and that mechanical motion generates energy. So this is where we get our conversion from the stored energy in coal to the energy that is now stored in a more usable form, electricity. Most coal burning power plants, though, are only about 35% efficient. So this is a big area where we could improve. Cogeneration is using a fuel to generate electricity and produce heat. So this would be if steam is used for industrial purposes or to heat buildings, it is diverted to turn a turbine first. So basically you are burning something, using it to turn the turbine, and then also using that heat energy to like heat a building or for some industrial purpose. This can improve efficiency to as high as 90%, which is huge. Going from 35% here to 90% can really change how much energy we're getting, which means we can overall burn less to do the same amount of work. Petroleum is a mixture of hydrocarbons, water, and sulfur that occurs in underground deposits. Oil and gasoline make this ideal for mobile combustion, such as vehicles formed from ocean-dwelling phytoplankton that died 50 to 150 million years ago. So you'll notice this is a little bit younger than our coal, which is 280 to 360 million years old. All right, so our petroleum, we have this estimate. This is Hubert's curve. This is estimating based on the production in barrels per year and how much we think we can produce from the ground. So production is kind of a weird way to look at it since you're mining. The prediction is a prediction of when we would run out. Now, petroleum does seem to be following Hubert's curve, this like theory. However, some of this decrease in production may not be due to not being able to mine it, but it may be due to things in the economy, changes in prices, people moving more into renewable energy, stuff like that. But this is showing that it's harder to mine, more costly to mine. So if it takes more energy to mine than the energy you're going to get out of that, you don't want to do it. And this is predicting, and this kind of curve has been used by a number of people after Hubert kind of created this kind of idea to estimate when we are going to run out. So this would estimate that we would run out of these things by, I mean, you can see here, it's now. We are not out of gasoline right now, right? It didn't go this steep decline. All right, so this is just kind of going over how some of this is extracted. So shale gas extraction methods, basically, this is what you may have heard of with fracking. So this is the hydraulic fracturing part. Here's our well. Here is the water table. So the water table is above, and then there's this mostly impermeable layer. You can shoot water, sand, chemicals into the well. When you inject the water into the well at high pressure, it can go down into this shale layer that contains this gas. It can crack the shale. As it breaks up the gas, it allows the shale, the rock, it allows the gas to come from those fissures into the well, and then the gas comes back up out of the well. This process, as you might imagine, is not super great for the environment because it can harm a lot of things, mostly related to Earth systems. So, for example, you may get contamination in the water table. Or because you are changing what's happening with the rock down here, you're breaking it, you can get increased earthquake activity. And that's what we've seen in places like Nebraska, where this kind of thing is done. Countries with the most petroleum are Saudi Arabia, Russia, the US, Iran, China, Canada, and Mexico. So Canada has a bunch of this kind of oil sands and oil shale. Oil sands are slow-flowing viscous deposits of bitumen mixed with sand, water, and clay. Bitumen is also called tar or pitch. This is a degraded type of petroleum that forms when a petroleum migrates closer to the surface, where bacteria can metabolize some of the light hydrocarbons and others can evaporate. So it's not quite as good as like petroleum, but it can still be usable. Oh, we already talked about the Hubert curve. So he predicted in 1969 that 80% would be used up within 60 years. We don't think that that's exactly where we're at, but this type of analysis is one that has been used again and again. He predicted peak oil in the 60s or 70s, followed by decrease. It seemed correct until recently when new techniques allowed us to mine oil that was previously unreachable. So the question here is, how much more technology can we get to reach other unreachable deposits? We just talked about fracking. Oops, and I got the state wrong. I guess it's Oklahoma that has done all the data. Because the fracking is happening in that general part of the U.S., I have a feeling Nebraska probably has increases too. But apparently the data just comes from Oklahoma. So erase that I said Nebraska. Risks and costs. So risks of this kind of oil mining. Environmental destruction. Oil prices are unstable. Shipping is dangerous and expensive. The Keystone Pipeline was not approved by Obama. Some sections have already been built. Keystone XL was approved by Trump. It was blocked by a federal judge in Montana in 2018. It is currently continuing in the courts. So we'll see what happens as we kind of move forward. Refineries are a source of air pollutants due to that it is recommended by some to use oil for other things, not for energy. So oil refineries put out more pollution prior to using it for energy. So because of that, people are saying, well, we should just use oil for things like paints or lubricants, other areas where we need oil to make a product, and not use it for energy. All right, natural gas, our third of the big three. This exists as a component of petroleum in the ground, as well as in gaseous deposits that are separate from the petroleum oil. Most often it's found in the Middle East and in the former Soviet Union, so Russia plus a couple other countries in that part of the world. It contains 80 to 95% methane and 5 to 20% ethane, propane, and butane. Largest uses are for electricity generation and industrial processes in the US. and other places it may have different breakdowns. It can also be used for residential heating, clothes dryers, stoves, and water heaters. And I don't know anybody who's had a clothes dryer that runs on natural gas in the US, but that's probably a bigger category in other countries. And I've only known a few people who actually use gas for heat. So it's not quite as common in the US as it is in other places. Gas can't always be shipped if it is found near oil and there are no shipping facilities. Sometimes it is just burned off. You'll actually see the well on fire and it's just being wasted. All right, so here are the life cycle greenhouse gas emissions by generator type. So based on what you're using, how many greenhouse gases are put out during the entire life of this product. So coal, the highest, then oil, then natural gas. And then down here we have our more renewable sources, with hydropower being the best. All right, I want to finish nuclear power, but I'm going to do that in a separate video so we can't kind of keep it separate from our fossil fuels, because nuclear power is its own kind of unique category.